If we have a regular heptagon where all 7 sides are the same length, we can work out an approximate but accurate value for the area by doing the following sum. 3.634 multiplied by a side length squared. But before working out the area of this heptagon in the example, we will look at how we come up with this sum by looking at this regular heptagon on the right side here. This regular heptagon is split into 7 equal-sized isosceles triangles. So firstly, if we want to know the value of the inner angles of each triangle, there are 360 degrees in a full circle, 7 equal-sized triangles. So the size of the angle here of each triangle is 360 degrees divided by 7. Now we will leave the value in its fraction form and we will look at one specific triangle from the regular heptagon. Now as we can see, this triangle has a height and it also has a base which is one of the side lengths of the heptagon. Now, the area of this triangle can be worked out the same way we do the area of any triangle, provided we know the base and the height, and that is by doing half multiplied by the base, also multiplied by the height. Now, as there are 7 of these triangles of equal size making up an entire regular heptagon, the heptagon area is simply what we have here multiplied by 7. So we're looking at a situation where we have the side length s given. So what we want to do is try and find a suitable expression for h, the height of one of these triangles. And we can start off doing that by splitting this triangle in half. What this does is give us a new triangle, which is a right angle triangle, where the base is now s over 2, and also the top angle here is now 360 degrees over 14 rather than 7. Now at this point we can recall that the tan ratio for an angle in a right angle triangle is the opposite side of the angle over the adjacent side. So we can look at our angle 360 degrees over 14. What we have, the opposite side is s over 2, and the adjacent side is the height h. We can make the right side a bit neater if we multiply the top and the bottom by 2. This gives us s on top and 2h below. Now the right side here can actually be flipped around if we write the left side as 1 over tan 360 degrees over 14. So we have 2h over s. Now at this point, to obtain an expression in terms of h only on the right hand side, we can multiply both sides by s over 2. And what that gives us on the left is s over 2 tan 360 degrees over 14. And what happens here is 2's cancel and the s's cancel, and we're only left with h. So now we do have an expression for h that we can use here. So we can multiply what we know for the regular heptagon area. So half multiplied by s, and now instead of h we can write this expression here. Of course multiplied by 7. Now multiplying all this out gives us the following. We have 7s squared on top, and below we have 4 tan 360 degrees over 14. Now we can write this with the s squared by itself. We have 7 over 4 times tan 360 degrees over 14 multiplied by s squared. Now this fraction has a numerical value which, rounded to 3 decimal places, is 3.634 multiplied by side length squared. So that is where this sum comes from, and why we can use it to obtain an approximate but still very accurate value for the area of a regular heptagon. So finishing off our example we started with, we have 3.634 multiplied by 36, and this gives us a value of 130.82 meters squared for the area of this regular heptagon. So if you have a regular heptagon in the future and you know the side length, you can just do this sum to obtain a good value for the entire area of the heptagon.